Okay, so hello everyone. I'm Sharon, Dr. Sharon Yaniv. Just to introduce myself, that's me when I was like 4 or 5 years old with my mom. I was born in Haifa, in Israel. I did my PhD in the Technion Institute in water engineering, and that's me. These are all my hobbies. I like very much to scuba dive, and that's me with my dog. I like mountain biking. These are my beautiful kids. The eldest is in the army, and I have he's almost 20, and then I have my daughter. She's 17, almost 17, and my youngest was 10 years old. And you can see some pictures taken here from near my house and in our lovely little country, Israel. So I will give, today I will give you a presentation. I think, in my opinion, it's very interesting. And most are not familiar with the phenomenon of the pressure transient search. And I will show you the relationship between leakage and pressure transient. So let's start with this video.
Wow. Oh my God. Oh, it's destroyed the back of his car. Is it safe to go close? Mon Dieu.
Okay, so oh my God, yeah, that's what can happen if you don't do the right protection to your system. You don't give the right protection to your system. So you see that big burst, what can happen, and the lots of water coming out. Okay, that's the leakage, the water losses that you may have in your system if you don't give the right protection. So all of you are familiar with the IWA standard water balance. We can see that the real losses, we have the leakage on transmission and distribution mains, leakage from overflows at storage tanks, leakage on service connections up to point of customer meter. And if we look at the component of the real losses, we have the leakage and overflows. Like I said, background leakage, reported burst, unreported burst, and excess or hidden losses. Okay, so you all are familiar with this and with the 4 components approach to management of real losses. I'm sure that all of you are familiar with the pressure management. You had many presentations on this topic. And you have the physical loss reduction checklist, change management focus, improve speed and quality of repairs, introduce active leakage control, review, improve operating practices, introduce network zoning and DMAs, practice pressure management, and apply good asset management. So all of you are familiar with this checklist. But how do you reduce the burst and leakage? Okay. And that's the topic that I would like, the linkage between the leakage and the burst, and how you can prevent those bursts by giving good protection to your system against pressure transients, which will cause a burst in your system. So I will focus on the pressure transients, explain to you what is pressure transient surges in the system, in order for you to understand better what you may have in your system and how you can protect and prevent pressure transients and the burst in your system, which will cause a leakage water losses in your system. Okay, so this often happens in many countries. You have bursts, you come, you fix it, okay? And you think that you have fixed the problem, but if you don't really fix and prevent the cause of this burst, it will, again, you will have a burst in your system. Again, you will need to come and fix the problem. I can tell you that a few years ago, when I was one of the conferences in the water loss task force conference, I don't remember exactly which country it was, I think in the Philippines, if I'm not mistaken. I heard someone giving a presentation of how he, a new concept of how to fix and repair the system fast. And then I raised this issue. I said, okay, he actually, we had like a small talk, and he said, you know, I came, I fixed the problem, and 2 weeks later, again, I faced the same problem of burst. So I said, of course, if you don't prevent this, the cause of the burst, it will happen again and again. Okay, so that's the main purpose of understanding what is pressure transient surges and how to prevent it. So what is surge? Is a sudden increase or decrease in velocity, flow rate, pressure producing transient conditions. What is sudden? T is the event duration, is less than 2L divided by C. L is the pipe length, and C is the celerity of the pipeline. Okay, what is celerity? Is the pressure wave speed. And of course, it varies by different type of pipe material. As you can see, the steel has the highest celerity, whereas the PVC has the lowest celerity. What causes surges? Shutdown of a pump, startup of a pump, pump trips. The pump trip is a worst case scenario. When I conduct surge analysis, the worst case scenario that I do is the pump trip. The pump suddenly stops, okay, and that will create a very high pressure transient in the system. Valve closure, valve opening, check valve operation. The check valve itself can cause a surges, pressure transient in the system. Rapid flow change, hydrant startup, shutdown, and pipe breaks. What is the influence of the surge on the pipes? Like you've seen in the 2 videos just shown you, you can see that big burst of water, okay? That can happen due to surges, pressure transient in the system. Okay, that upsurge can cause pipe burst, pipe fatigue, and the downsurge will cause a pipe collapse. And the surges itself can cause damage to pumps and other accessories in the system. In the pipeline, okay, we have, you can see around pipeline. There is always a weakened section in the pipeline. Okay, this is a weakened section. And when you have those changes, the pressure transients, it's not only one big occasion of a pipe burst that can cause this cracking and rupture of the pipeline. It's something that can take years until eventually you'll see the rupture. So you can have those small down surges and up surges in the system that will create the crack in the pipeline, and eventually that big rupture, that's the crack and the big rupture that you've seen in your eyes, the big burst of water coming out, and those water losses. It's not even a leakage. Okay, when you have a rupture, big rupture, that's already water loss. Those cracks that you have in the system, that will create those hidden losses that you have, that small leakage that you have in your system. Okay, and also the surges also can create a collapse of the pipeline. Okay, so you can see those upsurges that can lead to pipeline burst. You see those, lots of photos, lots of video of pipe burst, as you can see. And exactly what I told you, that you have a crack in your system, and something that years you can have this crack and this small leakage in your pipeline that it's very difficult to locate. This is why you have all kinds of new devices to locate those hidden losses. And this small leakage, after several years, can create that big burst. When you have this big burst, that's very easy to locate because you see the water coming out, you come, you repair, you fix it, and that's it. But those small leakage, and that's mostly what you have in your system, it's not something that it's hidden. It's not something that you can see and come and fix it very easily. It's very, very difficult to locate those small hidden losses, leakage, small leakages in your system. So the way to deal with this is to prevent this cracking, prevent those pressure transients in the system, the downsurge, the upsurge. You can see the crack here. That's the damage of that was created in the pump. Extreme low pressures can also cause a lot of damage. That's the collapse, the downsurge that they lead to the collapsion of the pipeline. That's taken from the US. That's from India. You see the collapsion of the pipeline. That's not a tunnel that used to be around the pipeline and just collapse inside in. The same like here in Venezuela. Okay, a steel pipeline that collapsed due to the downsurge. Okay, 72-inch steel pipeline collapsed. That's in Valencia. You see the collapsion of the pipeline, PVC pipelines. And that, some of you have seen in the Mythbusters crash bunker with vacuum. You see what can happen.
Come on! Come on, you melon farmer.
Okay, so that lots of damages that you may face if you don't give the good protection to your system. This story happened a few years ago. It was in 1998 in New York City, Fifth Avenue. In between, it was at the first, January 1st. Usually in January 1st, but the Americans, they like to watch during the day football matches and drink Budweiser. And during the commercial, everyone, they need to run to the toilet and take out the Budweiser. And what happens is that you have all along the day, you have like a downsurge and an upsurge. Why? Because during the matches, everyone watches TV, and during the breaks, everyone runs to the toilet and flushes the water at once. So that in that day, you have lots of small pressure transit, downsurge, upsurge, and eventually what happened is a big burst of water, as you can see here, this picture, the Fifth Avenue was completely flooded with water. And if we look, that's the street cross section. That was the 48-inch water main pipeline. And you can see that's a 48-inch pipeline. You can see what happened. As you can see, this is a very old pipeline, but exactly what we said, that this occasion of the flooded of, lots of flood of water coming out, big burst of water coming out from the pipeline, that's something that happened after many years. And you can see exactly what we mentioned, the crack on the pipeline, you see the crack, and the rupture. So that took several years. You had that downsurge, upsurge, and you had the crack inside the pipeline. And eventually that one big occasion of that rupture that flooded the street. So what exactly happens in our system? Imagine you have a locomotive and the railway wagons. And when we start the pump, when we start the locomotive starts moving, it starts abruptly, begins to operate, okay? And bam, the locomotives go abruptly into the railway wagons. The same thing with the pump, the water abruptly starts moving. The fluid goes bam inside that static column, water column. That's when we start the pump. When we have the pump shutdown condition, like I said, that's the worst case scenario. What happens? The locomotive suddenly stops moving. The railway wagons, they move forward due to inertia, and then they come back and bam, slam into the locomotive. That's exactly what happens with the pump. The pump stops, suddenly stops, could be due to electric power failure, and the water column moves forward and returns back and slams into the check valve. Okay, that's what we call the water column separation. And that's the worst case scenario. The water column separation is a downsurge followed by an upsurge, okay, resulting from a pump trip. We can see diagram A, that's near the pump discharge. And diagram B is 8 kilometers downstream the pump. We can see that the same phenomenon of a downsurge followed by an upsurge happens not only near the pump station, but also along the pipeline. So the protection is not only given near the pump, but also along the pipeline. We can see what happens to the system. That's an animation that will show you the water column separation with and without protection. So we have the pump intake. Okay, the pump is working and suddenly the pump stops. What happens? You see, we have the water column separation. Water moves forward. Okay, we can see the downsurge. The pressure goes below the vapor pressure. Okay. And the water column returns back. Okay, the pressure goes above the vapor pressure, high pressure spike, and bam, slams into the check valve. See high pressure, and you see the burst. Okay, and by placing one of the solutions, placing a non-slam air valve. Now, when you have the water, when the pump stops, okay, you have the water column separation. What happens here? When you have the water column separation and you want to avoid that downsurge, okay, the air is being admitted through the air valve to eliminate that downsurge. And when the water column returns, water column returns, then the air goes out slowly from the non-slam device, and you don't have that high spike of pressure. And soon I will explain what is a water column separation, how this collapsion occurs and how we can avoid that. Okay, so that's the water column separation and cavitation. You can see what happens due to the cavitation. Another reason for having surges is valve shut-off condition. Okay, the railway wagon and the locomotives, they move forward. You have a wall and the railway wagon, bam, slams into the wall. All the wagons, bam, slam into the locomotive. And that's exactly what we have in our system. The water slams into, could be a valve, okay, and creates a high spike of pressure. So we can see here in this diagram an upsurge followed by a downsurge. Upstream of a closing valve. Okay, we close the valve. You can see the upsurge. Okay, and what happens is the upsurge is followed by a downsurge. And when this vapor cavity collapses, it creates a very high spike of second upsurge, which is higher than the first one. And soon I will explain exactly why this happens and, of course, how can you avoid that. So that's the formation of the vapor cavity, and when that collapses, creates a very high spike of pressure. I would like to show you a video of experiment that has been done 20 years ago in Fraunhofer Institute in Germany. The experiment was conducted by Dr. Ludwig from Fraunhofer Institute, who has approached us to do an experiment. They have developed an isolating valve which can be controlled. The closure of the isolating valve can be controlled. And they were anxious to see, controlling the closure of the isolating valve helped them reduce the upsurge, but they had problems with the downsurge, and they wanted to see the combination between the isolating valve and the air valve and see how it reduces both downsurge and upsurge. So we did this experiment. Okay, that's the isolating valve. Those are the places where they place the air valve. The flow is from left to right. They did the experiment with a very high velocity, 4 meters per second, in order to create that high spike, high pressures, the pressure transient. And I would like to show you this video. This video was taken in this experiment without any protection, okay? Only closing, sudden closure of the isolating valve. What I would like you to see and hear is what happens when they close the valve. You will hear the water column separation. You will hear the water column move forward and returns back. The slam, okay? And you will see how the pipeline shakes. Now, this pipeline is a steel pipeline with a very high wall thickness, so please don't try it at home. And that's the reason why it didn't burst. But as you know, in waterworks, in the water systems, this is not a pipeline with such a high wall thickness. So if this had happened in a regular system, water system, the pipeline would have burst.
Stationäre Flüssigkeitsgeschwindigkeit 4 Meter pro Sekunde, ohne Bremse, ohne Rückschlagarmatur.
Okay, that's the isolating valve. Close it. That's the sound.
Vier Meter pro Sekunde, ohne Bremse, ohne Rückschlagkörper.
Okay, so move downstream, same phenomenon. Okay, close the valve. You see how the pipe shakes.
Stationäre Geschwindigkeit 4 Meter pro Sekunde, ohne Bremsanlage, ohne Rückschlagklappe.
First, upsurge, second. See how shakes, moves. Like my more thickness of this course, this is the reason why it does that. Okay, so the graph shows the red is with what you've just seen in the movie without any protection. You see more than 40 absolute bars. Okay, very high. With protection, it went down below 10 bars. Okay, so you see that big difference between with and without protection. And that's very easy. Like I said, the prevention of those pressure transient, it's very easy to prevent it by giving the right protection in your system. You can see this video showing the water column separation in the ocean. That's what we have in the system. You have the water column separation. And this is the most interesting video, in my opinion, that shows in slow motion the formation and collapse of a vapor cavity. So just before I show you this video, I would like to explain what's happening exactly. What is the water column separation? What happens is, as you know, at what temperature does the water boil? In one absolute pressure, it boils at 100 degrees, right? But you need to understand that for each temperature, you have a different vapor pressure, okay? So if the temperature of the water is 20 degrees, the vapor pressure is around 0.2 bars, absolute bar. It means that when the pressure goes below this vapor pressure, what happens? The water boils. The water performs from liquid to vapor. Okay? And that's when you have that pump trip, okay? You have that downsurge. Downsurge meaning that the pressure went below the vapor pressure. You have the formation of the vapor cavity. And when the pressure goes above the vapor pressure, okay, that is when you have that collapsion of the vapor cavity. And that's when you have that high spike of pressure. Now, this happens very, very fast. This is why you have this slow motion video that shows you. You can see the time. And you see that it happens very fast, less than 1 second, you know, everything happened, the formation of the vapor cavity. And that's why the protection that you need to give to the system needs to react very fast. When you have that formation of the vapor cavity, you need very fast to admit that air to avoid that vapor cavity or water to avoid that vapor cavity. So let's look at this very interesting video. You can see the time. Okay. You see the formation of the vapor cavity. You see the liquid transforms into vapor. The pressure goes below vapor pressure. So we have the formation of the vapor cavity. Not even 1 second. Okay, you see that's a vapor cavity. Not even 1 second has passed. Okay, so we have this vapor cavity, the downsurge. The pressure went below the vapor pressure. 1 second passed. Now the water column returns. What does it mean, the water column returns? It means that the pressure goes above the vapor pressure and the vapor transforms back into liquid. And that's when you have that high spike of pressure, okay, the upsurge. As you can see, not even 2 seconds. Okay, so that's something that happens very, very fast. And you must give the right protection to your system. Okay. So that's a water column separation, 2 seconds. Okay, so we can see a schematic description, what you've just seen. Trips, what you've seen in the video is that when we close the isolating valve, but that's same what we have in with the pump trip. We have the water column separation. Okay, the formation of the vapor cavity, the vapor cavity growth, the flow reversal. Okay, the water column turns back. We have the collapse of the vapor cavity and bang, upsurge. So how can we prevent those pressure transients, the surges? By slowing the change rate of velocity in the system, by slowing the rate of filling empty system sections, okay? When the velocity is high, the delta H, the pressure, the head will be, pressure will be very high. By releasing air at a slow controlled manner while filling a pipeline section, and to avoid the downsurge is by introducing air or water into the pipeline at points where downsurge vacuum conditions are expected. Now there are several devices that can help prevent that surges. Air valves, we have the non-slam air valves, vacuum breakers, dynamic combination air valves. We have the pressure relief valves, surge anticipating valve, rupture discs. I don't have time to go into each device, but just in general that that there are devices that can protect your system. By pump bypass line that have a check valve preventing backflow. They're activated when the pump suction head exceeds the discharge head and are useful for 2 reasons. They prevent high pressure buildup on the pump suction side, and they prevent cavitation on the pump discharge side. This solution is less advisable due to the check valve operation itself. Surge tanks, you have the one-way open surge tanks, you have the stent pipes, you have closed surge tanks, air vessels, we have the compressor vessels, bladder vessels, and hybrid surge tanks. Okay, so those are the devices that you can prevent the surges. So let's just summarize. Many water utilities ascribe their high seasonal burst frequencies to pressure transients. Pressure transients, as just shown you, cause cracks and unseen small breaks in varied pipeline, and that's the most. If you take the volume, you calculate the volume, the most water losses volume happens due to those unseen small cracks you have in your system, not those big bursts that you see, you come and fix. Pipe fittings and accessories and can also cause severe pipe ruptures and pipe bursts. These damages result in leakage, as you've seen, and result in financial losses and in water shortage, especially at times of water scarcity. Control of pressure transit can greatly reduce the formation of these damages and consequent leakage. So now you understand the linkage between the leakage and the pressure transients. So I'll open the video, and if you have any questions, please don't hesitate to ask someone else first. So please,
okay.
if you have questions.
Thank you very much, Sharon. That was very interesting to understand the dynamics of how surges happen and how they cause the leakage. As Sharon said, if anybody has any questions, they can ask them in the chat function. while we're waiting for people to type their questions in, I've got one is that upsurge, where you've got a high pressure, we tend to see that fairly frequently in terms of bursting of pipes and cracking of pipes. But the downsurge, where the pipe actually collapses, we don't see so often. Well, I've never seen it before. So I'm just wondering why you think downsurge is less of an issue. Is it because people protect the pipes more on the downsurge than they do for the upsurge?
I think they protect, yes, they protect the system more, the upsurge than with the downsurge. And it's, yes, it's less common to see a pipe collapse, but as I've shown you several pictures, it happens, even in the US and other places in the world. And mainly you can see it in the irrigation systems. In the irrigation system, you see many PVC pipelines that collapse and other.
So, but I suppose when in water supply, a lot of the pipes are steel for the large pumping mains. So maybe they're stronger, so you don't get so much of a downsurge issue.
Yes, that's also the reason. I've shown you a picture from Venezuela. That was also a steel pipeline that collapsed.
Yeah, I saw that, yeah.
Yeah, in most of the cases, most of the pipelines are protected, and they can, they don't collapse. They have a resistance for the collapsion of the pipeline.
Okay. We've got a question from Laszlo. I'm not sure if you can answer this, but he said, is there any instrument to measure transient pressure within 0.001 of a second?
I don't know if it's 0.001 second, but there are instruments that measure the pressure transient. Yes.
I think the devices that I've seen, they sort of record at something like 256 times per second is the lowest, I think is the fastest I've seen. So that would be sort of like 0.04. So yeah, there's a few devices that do it at 256. Maybe there's some that do it more than that as well, but there are devices out there that can record at such low, but maybe not as high as 0.001. Okay, we've got a question from Ian, which is, at the locations where transients are most likely to be generated, what data sampling rate and recording rate do you recommend to help identify transient activity and the true transient magnitude? So I suppose this is an inverse of the question that somebody was asking just now. Yeah.
Mm-hmm.
So what would you recommend as the frequency for logging?
Yeah, like you said, the frequency that you've mentioned could be efficient to locate, the transient, because it should have, very accurate, and the frequency should be very high in order to locate the pressure transit, because as you've seen, it's less than 1 second and it happens. So, and I know that we have done it. We've done some experiments on the pressure transducers that we have used were very accurate, and it's very rare to have use those pressure transducers. Very, usually the regular pressure transducer do not locate those downsurges. Okay, they can locate the upsurges, but not the downsurge.
So I know quite a few of the common data loggers, they go down to 1 second logging, but you recommend to go sub-second. It needs to be more than just one per second.
Yes. Yeah, 1 second will not locate the downsurge.
You're not going to pick it up. Yeah. Okay, we've got a question from Stuart, which is, where do you recommend starting with introducing clients to the issue of pressure transients?
I can tell you that in most places, what I do when I go around the world and giving presentations, it's mainly for you have to. The presentation should start in the designing engineers. They need to understand what happens in the system, what can happen, and they need to implement in the designing stage to perform the surge analysis in order to give the best protection to the system. This is exactly what we do. And I know it becomes more and more, I know here in Israel, for example, almost every designing company approaches us to do a surge analysis for every system in the designing stage. So something common today here in Israel, and it's becoming more and more common in other places in the world, because I get almost every day I get a request to do a surge analysis in the designing stage. Or it also happens in places where they have problems and they want to check why do they have those problems and which protection to give to the systems.
So Stuart sort of backed up his question with another one, and it's what if the clients don't think they have a problem? How do you convince the clients that they do have a problem?
First of all, not everyone has a problem, okay? Not every system has a problem, but convincing them is only by showing them the presentation that I've just shown you and showing them what can happen to the system if they don't give protection. I think that convinced them. I can tell you that in most places that I have been, after showing that presentation, they start approaching us for conducting surge analysis and checking their system. It's becoming more and more common, but the engineers, the design engineers, they must understand the problem in order to understand that they need to solve the problem and check if there is a problem in the system. Okay, I can tell you that in most of the cases, air valves that's mandatory in every system. Okay, every system, you must have an air valve to discharge the air when you fill in the system, introduce air when you drain the system, and during operation, you need to release the air. So that's something which is common in most countries. You have a air valve placed in the system. And in some, when I do the surge analysis, some of the system, only by placing air valve, that solves the problem. You don't need any other protection. The protection by placing air valve, that's efficient. But some cases, you need to give more protection. It's not the air valves are not enough, and then you need to give either pressure relief valve, pressure anticipating valve, surge anticipating valve, or a surge lines. That's also something which is very common in most places in the world. So it's, of course, only by doing it, you can evaluate. I know that I receive many requests for surge lines to evaluate the size of the surge tank, and people don't understand that you cannot, it's not like you have the rule of thumb, okay, the pipeline diameter is this size, the flow rate is this, and by having the flow rate and pipe size, that's enough, and I can give you this, give you the size of the surge tank. No, it doesn't work like that. You need to conduct the surge analysis, check and see what happens in the system, and according to that, give the best protection to the system.
Okay. There is a comment from Ian. It's not really a question, but it's a comment, which is design is one thing, but actual operational practice is something else. So he always proposes to monitor at pumping stations where there is a history of leaks or bursts downstream of the pumping station. However, not detecting transients can also be good news, as it means the surge protection is working. So I think Ian is correct, and you're correct. One thing is to design it correctly and construct it to limit the surges initially. but then you need to make sure that they're operating it how it's been designed, and that can be done through monitoring of transients in the network.
I have a very interesting story to share with you regarding designing and in practice what happened. A few years ago, I was in Uganda, one of the pump stations in Uganda. The pump station was designed by a German engineer who has done the surge analysis, and he has recommended installing surge tanks in the system. Now, what happened is, along the pipeline, everything was okay, no burst, no leakage, worked perfectly. But near the pump station, the surge tank is placed near the pump station, very close to the pumps. They had a leakage. They had in the joints near the check valve, they had leakage, and they had small bursts. And they were amazed because they placed the surge tanks. They gave apparently the best protection to the system, and they didn't understand why. So what happened? We came, and what we discovered is that that German engineer hasn't designed, even if you do conduct a surge analysis, you need to design properly the devices. He designed the outlet, okay, the outlet of the surge tank was for water system, was as the same size of the pipe diameter, and it was 900 millimeters. Now you can imagine an outlet of 900 millimeters, that water column that returns back to the pump station and bam, slams into the check valve, which the check valve itself was a poor check valve, not a good design check valve. And that created those small bursts. By changing the outlet size, reducing it, they solved the problem. Okay? So even if you do the surge analysis, you need how to design properly the device itself. So that's...
Okay, I noticed when you were talking about the different solutions for helping with surges, you were talking about valves and surge vessels, but you didn't mention variable speed drives. So that they seem to be more common these days, that pumps have variable speed drives to help soft start and soft stop the pumps. Would that be something that's useful?
That's true. Of course, that's useful, but that's not the solution for pump trip. Okay, there is a difference. Like I said, when I do a surge analysis, I go for the worst case scenario, which is a pump trip.
Okay,
the pump
where power goes off. Yeah.
Power failure. Okay, so
yeah. Okay. Well, thank you very much, Sharon. We don't have any more questions, so thank you for your presentation. Very interesting, and thanks to everybody for listening in and the questions that we received.
Okay. Thank you very much.